Here we go. So, you do not have these limits on your paper. I just wanted to run through them real quick. Okay? You see the first one is x going to infinity. I'm asking you what the end behavior is. There's a fraction. I told you when you have that, you want to look at the biggest thing on top and the biggest thing on bottom. But when I say that, I mean terms. Things are separated. Things that are separated by pluses or minuses. Cool? So the biggest thing on top is really this entire thing, sine x times ln x. All right? Now, I know you don't like ln of x, but sine x is just going to keep going up and down. That's all it does. And ln of x gets bigger, 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 but it does it very slowly. ln of x looks like this. Cool? That's what ln looks like. Compared to x, which is in the denominator, that's what y equals x looks like. Which one of those is going to get bigger faster? X. And if the bottom gets way, 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 way bigger than the top, even though sine's bouncing back and forth, guess where that thing's going to go? To 0. So even though it looks scary, that's not too bad. That's a 0, okay? And the second one, as x goes to infinity, this is a nice one, because the top's going to go to, where's e to negative x go as x goes to infinity? It's going to go to 0, and the bottom's just going to get huge. So we have very tiny numbers over very big numbers. That is also 0. What's wrong, pen? Okay, great. The conditions for continuity, we discussed this, are number one, the limit has to exist. And the way you say that is that the left-hand limit, and we're writing this in symbols, and the right-hand limit are the same. Note the f of x's that are next to the limits. Not on the left side of them, on the right-hand side of them, kids. Okay? That right there guarantees the limit exists. That means both sides are going to the same place. That looks like this. Right there. But in order for it to be continuous, this has to equal f at a. There has to be a point there. Okay, that's continuity. That's the whole basic idea. The left side and the right side go to the same place, and there's a point there. Sound good? Hello, Maya. How many papers on your desk, Maya? Great. Here you go. Okay. So, there's really only 3 things that you have to worry about continuity. I think continuity is one of like the easier things that gets overcomplicated. There's 3 things in math we cannot do, okay? Which is undefined, I guess. Not we can't do. One of them is divide by 0, okay? So if you ever have 0 in a denominator, that means the function is discontinuous there. Does that make sense? We also cannot take a log of anything negative or 0. So if you have a logarithm and the argument, that's the inside thing, is ever negative or 0, then that graph is not continuous there because there's no points, okay? Oh, Sean, you got to go. Oh, no, Miss Dolan's going to email you something. Never mind. Square roots. Whatever's inside of a square root, the argument has to be positive, okay? So let's just take a look at these real quick. When I ask you where is it continuous, the easiest thing to do is think about where is it not continuous. Where's number 1 not continuous? 3 and negative 3, right? 3 and negative 3, because then we would be dividing by 0. It doesn't matter if they cancel out, if there's a hole, that's all limit crap. Continuity is just, if I plug in an x value, do I get out a y value? Okay? So it is not continuous at negative 3 and 3, which means I asked you where is it continuous. It is continuous, starting all the way from negative infinity, all the way up to negative 3, and then from negative 3 to 3, and then from 3 to infinity. That's how you'd write that. Okay, so from left to, all you have to think about our x number line left to right. Negative infinity is on the left, and it's continuous all the way up until we get to negative 3. Cool? That's the same exact thing as writing, and I think interval notation is better, but that's the same thing as writing this. Oh, it's continuous, all real values, except for at positive negative 3. That's all we're doing. We're taking out 2 numbers from the real number line. Okay? Okay. Number 2 looks a little scary, but where is it not continuous? Just 0. It doesn't matter. Sine is continuous everywhere, right? X is continuous everywhere. So when you multiply them together, that's continuous everywhere. Cool. The only thing we have to worry about is we can't divide by 0. So that 1 over x causes a discontinuity at 0. So it is continuous from negative infinity to 0 and from 0 to infinity. Sound good? Number 3. A little bit weirder. Okay, I know you guys don't do a lot with logs, but I'm telling you, if you see a logarithm in a function and you're asked where is it continuous or where is it not continuous, you just got to make sure the inside thing is not 0 or negative. Okay, that's it. Basically, it has to be positive. So let's take a look at something easier. What if it was just log of x? And I want to know where that's continuous. I need the inside thing to not be negative or 0. So x would just have to be greater than 0. That would be from 0 to infinity, right? That's an easy one. That happens, by the way, because a logarithm graph looks like this. It never hits 0. It never goes past 0. Okay? That's what a log looks like. It's just an exponential, which most people know what that looks like, flipped over. Okay? Okay, but what if I did something stupid like this? X squared. Well, just 0 is not continuous now, because x squared is always positive. You know what that looks like? It just forces a piece to come back here like that. Okay? Because now all the negative numbers can get plugged in, but they look just like the positive numbers. Okay? If I put, like in the question that I've asked you right here, an x squared minus 4, this is our question right now. I need x squared minus 4 to be greater than 0. I hope that is very clear at this point. The argument of a logarithm must be positive. Okay? Log of a negative doesn't make sense. It's like square root of a negative. But worse, square root of a negative, we can at least talk about imaginary numbers. Log of a negative, there's no imaginary numbers for that. There's nothing. It doesn't equal anything. Okay? It's non-existent. It's like dividing by 0. It's not a number. So I need it to be positive. One way to tell where a graph is positive, like x squared minus 4, is to factor it, if possible, right? And graph it. So again, I'm not graphing the log thing. I'm graphing the inside thing to see where it's positive. X squared minus 4 has zeros, and you probably already know this, but it has zeros at negative 2 and 2. Okay, and we know it comes down to negative 4, if you think like that, and it's a parabola that does this. Now that function's continuous everywhere, but I'm taking the log of that function. This thing will be continuous as long as it's positive. You see where it's positive? Right here and right here. That make sense? So we're going to say it's continuous from, hello, sir. Yes, 3 passes. Cool. Okay. So we're going to say it's continuous starting at negative infinity, because that's where x squared is positive, all the way up to what x value? Negative 2. Can we include negative 2? No, because that would make it 0 inside, undefined. Union with 2 to infinity. How do you feel about that? Pretty good? That's our whole concept of continuity, basically. And the only thing you got to worry about with continuity, really, so look, we did the log, we did the division by 0, is what if instead of a log of x squared minus 4, we had the square root of x squared minus 4? That's almost the same question as the log of x squared minus 4. Cool. You just want to come in and say hi. I get it. All right. Who is this? Angelica and Sean. Boom. Sean passes to Angelica. All right. The answer to this question, again, because I need that inside to be positive, is still from negative infinity to negative 2. But now I can include negative 2. Because I can take the square root of 0. It's 0. Okay, so logs and square roots are very similar. All right, you just can't have the inside be negative. The only thing is square roots can be 0 and logs cannot. Okay, so if that was the function, it would look like this. That'd be where it's continuous. Okay, well, that's just where the graph exists, basically, if you were to graph it. Okay, okay. Actually, what that graph looks like, the x squared minus 4 graph, is it's 0 here and it just goes back like that, and it's 0 here, it just goes out like that. Okay? Okay. You don't like that? Okay. Here's a cool graph I gave you. I made that up all by myself. And my question is, where's it discontinuous? If we start from left to right, where's the first place it's discontinuous? X equals negative 5. And when I ask you why, a lot of kids are like, because it's not connected. That's not what I want. I want using our definition of continuity. Which part of that fails? It is so true. I know the camera can't hear you. But what Haley has said is that the left-hand limit and the right-hand limit are not equal. Make sense? Matter of fact, the left-hand limit and the right-hand limit, even though we're going to say they are negative infinity and positive infinity, Miriam, you all right back there? What are you doing? You're on the phone a lot. Is when we say it goes to infinity, that really means there is no limit. It's not approaching a number. Okay? But also, there's no point there. So we can also say neither one of those is equal to f of negative 5, because f of negative 5 is undefined. That makes sense? So all three pieces of our continuity fail. The next place it's discontinuous is negative 4. But that fails. The limits exist there, right? You see that. That's a hole. But the limit and the y value are not the same. That's why that fails. So you would write, oh, that's because, and there's not a lot of room in here. This is annoying to write in there. But the limit as we approach negative 4 is not equal to the y value there. That's f of negative 4. Can I zoom in any further? A little bit. Okay. Oh, now I can't see the graph. We go in that? Negative 1 is the next one. And that's because the limit as I approach negative 1 from the left is not the same thing as the limit as I approach negative 1 from the right. There's a point there, and it equals the left-hand limit, right? The left-hand limit's filled in. However, the left and right limits are not the same. Make sense? And the next one is at 2. Is that okay? So x equals 2. And all you got to write really is that, look, we can write this simple. F of 2 is what? So it's undefined. Yeah, if a function's undefined, it can't be continuous, right? So f of 2 is undefined. And if it's undefined, it cannot equal something. Does that make sense? So I'm not going to ask everything we just did, I'm not going to ask a question like that ever. Okay, I just want to make sure you get this concept of continuity down. Cool? So there's a difference between the left side, the right side, and the point. I'm going over that over and over again. All right. The next question, number 5, is something we've been over, and I won't ask you where is it continuous or discontinuous. I'll ask you like I've done before, does the limit exist? Okay, I might ask if it's continuous or not, I guess. But we've been over these piecewise functions right away. I mean, a lot. And right away, I'm hoping you see, what is there not at 1? Do you see how x is less than 1 is the first break? There's no equal sign, which means there's no point. Does that make sense? Okay, so this thing's not continuous at x equals 1 because f of 1 is not defined. Oops, not equal to 1. Not defined. There's no point there. Can't be continuous. Yes, ma'am. You get the same thing, but there's no point there. That means at 1, they're both going to 5, but there's no point there. Okay, that's a hole. Okay, so we have multiple ways to talk about this. They all really mean this. Like a hole means that there's no point where the two graphs meet. Okay, a lot of similar ways, or a lot of different ways to talk about similar ideas. The next possible place would be at 2. So the first thing we check is the left-hand limit. That has to do with the inequality. I'm basically just plugging 2 into here. What do we get? 16, 18. Yeah? Another way of saying that is the limit as I approach 2 from the left of f of x is 18. Okay? As I approach 2 from the right, I'm looking at this piece. I've put a 2 in there. I get what? 18. Oh, that's nice. So that does happen to equal the limit as I approach 2 from the right. So what that means is that either this thing is continuous or there's a hole. We know both sides are going to the same place. There's only 2 things that could happen. There's a point there or there's not a point there. So to check that out, I got to check x equals 2. I put a function in there, but the function doesn't matter because there's only 1 point on it. It's a 2. If I put a 2 in there, I get 9. Make sense? So both go to the same place, but the point is not there. So it's not continuous at 2 because the limit as I approach 2 of f of x, I don't have to talk about left and right because they're both the same thing. That's what that means. Is not going to be equal to what f of 2 is. And that's a hole. Make sense? So for homework, here's what I'm going to ask you to do. We're going to do a couple in class together here. I'm going to say, when I say extend each function, I mean if you can add 1 point to this function to make it continuous, do it. Okay? An easy example of that was the multiple choice question we had the other day. We had x squared plus x over x. Okay? That's discontinuous at 0, right? I can't put 0 into that. But it reduces all the way down to x plus 1. I can make that, not make, I can put 0 into that. I get a 1. All that means is if you were to graph this, there's a hole at 0 and the y value is at 1. So if I want to make it continuous, I'm going to plug a point right in at 0, 1. Make sense? The way you would do that is you're going to make up a function. I know this seems weird. I really just want you to understand holes and such. And you're going to say, hey, that's what f of x is everywhere except for 0. Because that's one point I can't plug in. But if at 0 I define it to be 1, does that see what I'm saying here? We plugged in the hole. Now that's a continuous function. Is that okay? You can only do that if it's a hole. If it's a jump discontinuity, which doesn't happen often, guys. For me to make a jump discontinuity in a graph, I either have to make 2 different pieces, or I've got to use absolute value or something weird. Okay? There's not a lot of functions that jump. All right? That's why when I make a graph up, I got to put in all these different functions to make it jump. I got to go in the Desmos and put in all different kinds of weird functions. Everybody see what I'm doing here? Try number 7. What point are we missing? What's that reduced to? X plus 2. Okay? Except I can't plug 2 into my original thing. Right? So this reduces to x plus 2. That's what we're thinking about. Except for at, oh crap, 2. Everybody okay with that? So, to make this continuous, all I got to do is add in the point 2, 4. 2, 4, because that's where that graph should go to. X plus 2 is going to be at 4. Okay? So to make this continuous, I'm going to make up this function. I'm going to let this be what it was, except for at 2, because it's undefined there anyway. And at 2, I'm going to make it equal 4. Okay? Graphically, what we just did was took a function that looked like this and said, let's just put a point right where we want it to be. Great. Is that okay? Okay. I think the most important question on this paper, you can try the rest. What do you know about 9 real quick? What's happening at 2? A vertical asymptote. You can't make that continuous, okay? So that's what I mean. Like, you can only make it continuous if there's a hole. But really, the big picture is the limit exists if there's a hole. I've been super redundant about this since like day 1, okay? If there's a limit exists, there could be a hole, and you can plug it in if you have to. But really, I just want you to understand a hole means a limit exists, okay? But either way, 9 you're going to write cannot be made continuous. There's a vertical asymptote, okay? All right. All the other ones should work out except for 11. Check out 11. That's a little weird one too. Yeah, man. Where's sin x over x undefined? I graphed this graph for you multiple times this year. It's undefined at 0. Remember this? But what's it approaching as x approaches 0? 1. I'm not going to do the whole thing for you, but the graph just looks like this. So what point do I need to add in to make it continuous? 0, 1. That's it. Make sense? All right. I do want to talk about 13. Okay, 13 is one I'm going to ask you. It's on the test review. I'm going to ask it on the test. One just like this, okay? We've seen one like this before, but this is going to be like a system of equations set up. So, if you see a function like that and you're asked to make it continuous everywhere, where are the possible places this thing could be discontinuous? Where's the first one? -1, and the second, 2. Okay? I need to make sure that the first piece, that top piece, whatever it happens to be at -1, has to equal the middle piece at -1. Is that cool? They got to be the same y value. So all that means is you're going to plug in -1 and set them equal. Cool. If I put -1 in the top thing for x, I'm going to get -a minus b. So this, again, is at x equals -1. Everybody okay with that? I drop -1 in there. If I put -1 into the second piece, I'm going to get 2. The problem with that is that doesn't tell me what A and B are. A and B can be infinitely many things at this point as long as that thing equals 2. Okay? So I've got infinitely many answers so far. However, my second piece has to be my third piece at 2. So if I put a 2 into the second piece, so I'm going to write at x equals 2. If I put a 2 into that second piece, I'm going to get 5. And that has to equal the third piece at 2. Remember I said it's like handing off a baton where the one stops, the other has to continue. Okay? So at 2, that thing equals 8b minus 2a. Everybody okay with that? And now I have a system of equations. We're going to solve that by substitution. I don't care which one you pick. I think picking the first one is easier, so I'm going to pick the second one just to show you what it looks like in case you get stuck with fractions. Again, first one's much easier. Both work. Okay? I'm going to solve this one over here for A. Okay? If you solve this for A, you get A is 8b minus 5 over 2. If you get A by itself, that's what you're going to get. Which, by the way, is the same thing as 4b minus 5 halves. Doesn't matter which one of those you use, they're both the same. If I mess up, please let me know. I think that's right, right? Minus 5, if I ever divide 2, yep. Easy enough? I'm going to take what A is, and I'm going to drop it into the other equation. Okay? Consistently, every single year, kids can set this up on my test. They can set it up. But it ends up being fractions in it, and like 75% of kids cannot solve it correctly. And all it is 2 lines, okay? So I'm not just putting it out there. I was very happy. You guys are the first class ever for every single body or every person in here got the limit as x goes to infinity of arctangent on the test or the quiz. Good job. Usually like a handful of kids miss that. So excellent. Nice work. Either way, I'm going to take that little thing, what A equals, and I'm going to drop it into the other equation. Okay? But when I plug it in, I'm going to put it in parentheses. So that's negative A minus, whoa, no. Come on now. Negative A, which happens to be 4b minus 5 halves minus b is 2. Everybody okay with that step? Just plug it in. And now I got to solve it. So this is the same thing as negative 4b plus 5 halves minus b equals 2. If you have fractions, kids, one thing you can do is multiply everything through to get rid of them. I'm telling you, on the test, there's going to be like over 7s and weird stuff. Okay? Multiply everything by 7 or something. Get rid of the fractions. In this case, I'd multiply everything by 2. Again, you don't have to do it. It makes it easier. That makes negative 4 become a negative 8. It makes 5 halves become a 5. And it makes negative b become a negative 2b. And it makes 2 become a 4. Is that okay? It simplifies the equation out immensely. Then you can easily see that negative 10b is negative 1. So b is 1 divided by 10. Sound good? But I didn't ask you what b was. I asked you what A and B are. A is 4 times 1 over 10 minus 5 halves. That's 2/5 minus 5 halves. Y'all with me? That 4/10 reduces to 2/5. Actually, reducing it was not a great plan because I got to get my common denominator back out to a 10. This is the same thing as 4/10 minus, what's this? 25/10. 4 minus 25 is negative 21. So A would have to be negative 21/10. And if that happens, then my graphs will meet. Make sense? So I did part of your homework for you already. On Monday, we'll do another one of these practice ones like that, okay? But you're definitely going to see a question like that on the test. Sound good?